So, for the most far-off worlds, we're thinking back in time nearly to the Big Bang. Envision gazing toward the night sky just to find it void, no stars, no universes, just obscurity. Now imagine a scenario in which we tell you this wasn't simply an illusion of the imagination. Imagine a scenario where we tell you that over 700 trillion stars disappeared from the universe, leaving researchers astounded and the world in amazement. But wait, there's more. Some phenomena arose from this grand void, something beyond our most stunning imagination. This isn't your typical infinite mystery, rather, this revelation will put to the test all we already believe to be true about the universe. We will embark on an adventure into the depths of space, where the unimaginable becomes possible, and the impossible becomes real. Are you ready to wander into the unexplored realms of reality? Join us as we unravel the mystery of how more than 700 trillion stars suddenly evaporated and the remarkable phenomena that arose in their wake. Stars don't mystically blur away. Today, stargazers have held the view that celestial lights are static and unmoving. For quite a while, astrophysicists have long expected that, even after it became evident that these lights were real objects like the Sun, they undergo very slow, dramatic changes over millions or billions of years. Cosmic explosions are the undeniable celestial signals that mark the death of the most monstrous stars in the universe. These stars are usually heavier than the Sun and undergo unexpected and catastrophic changes as they reach the end of their lives. The explosion should be visible for eons and could be detectable across countless light years. Consider the possibility that, by and by, some stars suddenly blur into insignificance. This seems impossible given what we know about stars. However, a group of stargazers has been examining data from many years of observations to determine whether the seemingly inconceivable does, in fact, happen. Tracking down objects that shouldn't be practical is the mission of an international team of cosmologists. Beat Rick Vill of the Nordic Institute for Theoretical Physics in Sweden said, "We're interested in a wide range of disappearing objects, but ideally, I'd like to find a star that has been consistent and has been there overhead as long as we can remember. One day, it just evaporates, and you can point the greatest telescopes on the planet at it and not see anything there." Since Vill and her colleagues began their work on the project in 2017, they have attracted much attention from researchers who see the potential in examining notable records. We have cosmologists from various fields interested in the project, experts in dynamic cosmic cores, the power source of brightly shining quasars in the distant universe, celestial physicists, and more. "Everyone has their reasons for getting involved," Vill said. "That doesn't mean all stars stay bright all the time. However, our current data suggests that stars change very slowly, and sudden vanishings should leave evidence behind. The sky is truly overflowing with stars that might be expected to beat and vary in brilliance." Vill emphasizes, "We're talking about something different. We know that there are factors, but their timescales tend to be a few years at most. We want to find something that goes from a completely stable star to just disappearing altogether." The emergence of fully automated telescopes over the last few years has allowed astronomers to survey the sky at an unprecedented rate. Mount Palomar in California is home to the ZTF, Zwicky Transient Facility, which is a combination of the historic Samuel Oskin telescope with a state-of-the-art camera. It can scan the Milky Way twice daily and cover the entire Palomar sky in just 3 nights, thanks to its incredibly wide field of view. This significantly enhances the likelihood of spotting drifters, which are sudden eruptions of light that can originate from distant stars, solar flares, or be linked to intriguing cosmic events like gamma-ray bursts. Projects like the ZTF work on extremely brief timescales, but if you have a rare event where something disappears from the sky like clockwork, then you really need to look over a longer timescale. In our case, we need to find a star that has evaporated or, in fact, seemed to have done so using as vast a time frame as possible, combined with the best catalogs from older times. Phil notes the distinction between the two types of star discoveries, emphasizing that their quest for reliable historical data took them back to Palomar and the Samuel Oskin telescope. This specific telescope had previously provided visual plates for an all-sky study in the 1950s. The U.S. Naval Observatory has scanned data accumulated from this comprehensive survey, while the rapid response system at Hawaii's Hubble Observatory was used to create a modern analog that yields data. There are various practical options. The idea is that interested parties might visit the site to evaluate the photographs, and if they have any inquiries about a specific sample, they can post a comment. The team needs to check and examine all objects in the USNO inventory that are marked as having no obvious known stars. They then check the shape, brightness, and other properties to see if it's an imperfection in the original study. The Gaia mission, operated by the European Space Agency, is currently gathering precise data for over 1 billion stars in the Milky Way. The team also analyzes candidate data with this information. Despite the lack of an ideal counterpart for a disappearing act by a stable star, many of the observed candidates are intriguing in their own right. The survey has so far revealed over 800 stars that are seemingly missing. Many of these stars still require further processing and in-depth study. Some brief transients have been studied and found not to be supernovae or other phenomena. These transients comprise most of what we have discovered so far, but there are still many uncertainties. Vil continues, the other less plausible possible outcomes are variable stars, destructive factors, or novae, which are explosions on the surfaces of white dwarf stars in binary systems. None of these sources are located close to a known variable, and certain advanced surveys should identify the companion star in a nova system, even if the white dwarf itself is undetectable. Inestimable emissions will momentarily become apparent as their energy yield diminishes, suggesting that they might be optical phosphorescences from gamma explosions or quick radio blasts, which are still inadequately understood. Such blasts are supposed to have incredibly huge amplitudes of roughly 8 to 10 extents, however, they vanish after a few moments and do not seem to have any distinguishable counterpart when we examine the same regions with large telescopes. Clearly, there is still a part of the work to be done with 800 competitors, and it's possible that a different assortment of objects, Val notes, if those 800 competitors end up containing an ideal evaporating star, could be the explanation. A failed cosmic explosion could be one possibility. This would be a Noali star whose core is so dense that it collapses into a black hole, gobbling up the star's outer layers in the process. The star would then no longer undergo the nuclear fusion that normally accompanies a cosmic explosion blast, leaving no noticeable leftover. However, it is not in that realm to favor this hypothesis. She establishes that such events should happen roughly like clockwork in our universe, presenting the chance of the Vasco project inadvertently finding one. Currently, other regular processes that could cause a star to essentially disappear are not effectively considered until a competitor with noticeable properties emerges. There is little use in speculating on possible new physics that could be associated with this vast disappearing act. Vell concludes that increasingly powerful computers and larger, more sensitive telescopes have ushered in the big data era of cosmology, leading some researchers to believe that the generally odd behaviors of stars and other objects are more likely to reveal the presence of extraterrestrials than radio transmissions sent our way, either deliberately or accidentally. The idea is that, as long as a society's advancement is far enough along, some of them will eventually figure out how to manipulate stars so that they appear different in ways we cannot explain. Vell cited the classic example of the Dyson sphere, a ring of power plants encircling a star, which would be the most efficient method for harvesting energy from a star. According to science fiction author Arthur C. Clarke's third law, any sufficiently advanced technology is indistinguishable from magic. In the absence of any known natural explanation for a star's vanishing, the intervention of intelligent extraterrestrials would likely seem the most plausible option. There are several different perspectives on this, Vell said. Dyson spheres and other structures might be turned on and off or pointed toward us for a certain time, or perhaps there are ways for a civilization to actually eliminate stars that are disrupting their activities. Even the red transients that the group has identified so far could have a potential artificial cause. For now, the first theories we pursue are our natural ones, and we have no reason to dismiss those. However, if I were in my extraterrestrial hypothesis mode, I suppose a laser beam could also create a red transient of this sort. In the meantime, the Vasco project is progressing with many of the candidates identified so far awaiting formal confirmation and analysis. Only a fourth of the sky has been checked thus far, and further advancement will hopefully be aided by more volunteer citizen scientists and new automation techniques currently being developed in collaboration with the Spanish Virtual Observatory. Cloak indicates exciting discoveries that have already arisen from the data and anticipate formal distribution. As far as we know, no process has ever been observed in nature where a star would just vanish, except for this theoretical failed cosmic explosion, Vell said. The primary motivation for considering disappearing stars was to search for the apparently unthinkable. At the same time, space-time openings might exist, however, humanity's telescopes cannot see them. If they do exist, they are incredibly ancient relics from a period soon after the Big Bang, when the universe had just begun to cool off from a hotter, more energetic state to the cooler, more stable one we observe today. According to this hypothesis, the Great Cooldown or phase transition began earlier in some regions than others, and bubbles of the cooler universe formed and proliferated across space until they merged with other bubbles. Eventually, all of space underwent this cooling process, and the universe disappeared. Some physicists have conjectured that the cosmic microwave background, CMB, may still contain hints of the old high-energy state at the boundaries of the bubbles where the space-time fabric was partially fitted, at the places where the cooling regions crossed, heat remaining from the tumultuous birth of the universe. However, as expressed in later analysis, such proof would be indistinguishable from background noise for any telescope to detect. A physicist from McGill College in Montreal, Oscar Hernandez expressed that grandiose strings are hard to conceptualize, yet they really do have earthbound partners. Have you strolled on a frozen lake? Have you seen breaks in the ice of a frozen lake? It's still very strong, nothing remains to fear. Yet, there are breaks. Ice is water that has gone through a stage change. Water atoms were free to move as a liquid and, afterward, out of nowhere, somewhere, they begin to form into a gem. As it advances, it starts to cover itself with tiles, which are ordinarily hexagons. Picture this: you have tiles that are unequivocally hexagonal, and you tile the lake with them. There is nearly minimal chance that your tiles will coordinate with those on the opposite side of the lake. Just like inestimable strings, the fishes develop through a stage progress component. Long fishes are shaped by imperfect gathering points on the surface of a frozen lake. These, in the texture of spacetime, produce vast strings. Assuming that the basic material science is valid, it is accepted by scientists that key power and molecule conduct are governed by fields in space, which were made during the underlying stage changes of the universe. There could be a field related to some molecule that needs to, in some sense, pick a direction to freeze and cool in. Since the universe is truly enormous, it could pick various directions in different pieces of the universe. He said now, if this field obeys certain conditions, then when the universe has chilled off, there will be lines of brokenness. There will be lines of energy that can't cool off. Those nexuses would seem like incredibly slender lines of energy going through space. Assuming that we saw them now, an extra piece of evidence that material science is more complex than the current worldview would be the discovery of those astronomical strings, which would be a significant arrangement. At present, the Standard Model consolidates not just the rudimentary particles, like quarks and electrons that form particles, but also more interesting ones, like the Higgs boson and neutrinos. It is viewed as the most progressive hypothesis of molecule physics that has been confirmed. On the other hand, the majority of physicists have the perspective that the Standard Model is fragmented and that there are different ways of broadening it, such as truly symmetric particles, also known as the Stash, Slepton, or superstring hypothesis, which states that all particles and forces can be described as vibrations of little multifaceted strings. Hernandez said many of the Standard Models that people, as a matter of fact, like a lot of superstring theories, also generally lead to inestimable strings after post-Big Bang expansion happens. So what we have is a product that is predicted by a lot of models. If they don't exist, then all of these models are precluded, and if they do exist, good gracious. Ronica of Meropolis School in Westmount, Quebec, and Hernandez had previously argued that the best method for identifying the strings in the cosmic microwave background, CMB, would be to utilize a convolutional neural network, an exceptionally effective pattern-finding algorithm. In a 2017 publication, they stated that if an ideal, noise-free CMB map is provided, a machine programmed with that kind of neural network should identify enormous strings with very low energy levels or pressure. However, getting back to the point in this new paper, they demonstrated that it's highly unlikely that we would be able to provide clean enough CMB data to the neural network to recognize these potential strings. Other brighter microwave sources mask the CMB and are hard to completely untangle. Even the most advanced microwave instruments have limitations in resolution and recording accuracy that shift randomly from one pixel to another. Combined with various factors, they found that this method is a dead end for searching for inestimable strings. Still, they expressed hope that things would end up good overall, utilizing measurements of the universe's evolution in early universe regions. Another technique for inestimable string hunting has been proposed, referred to as 8.3 power planning. Unlike past methods that depended on concentrating on individual system movements or exact CMB images, this technique relies on measurements of the typical speed of hydrogen molecules' division from Earth in all regions of deep space. The top 8.3 power planning observatories, named so because hydrogen's electromagnetic radiation has a distinct 8.3 MHz frequency, are not yet functional. However, the researchers expressed confidence that stronger evidence of astronomical strings will be found in their data upon their arrival. Once more, the inquiry can begin.